Welcome back to another exciting edition of ColaVision here on the Turtberg 67 network. Okay, so anyway, what we're looking at today is series and parallel circuits. And what I want to look at first, I want to look at this one single light bulb I've got hooked. And I've got that light bulb hooked to a lantern battery here. Nice Rayovac, little advertising. And so what I'm going to do is I'm just going to complete the circuit. So I've got this wire run from one terminal of the battery, and I'm going to post it over here to this other side. And we'll just go ahead and touch here, and when we do, we can see that the light bulb lights up. So what we want to think of, and we're going to think of light bulbs as being like a resistor, because in a way that's what a light bulb is. It's a resistance in a circuit. It takes electricity, it takes a potential, a voltage to get through that light bulb. So if we can think about this light bulb as being a resistor, then we can visually look at resistors in a circuit. So we just saw what happens when we have a single light bulb hooked up in this circuit. We make it light up. So now I want to do something. I want to take two light bulbs and I want to hook in what's known as a series. And so what makes them a series, sorry, I got some glare off the lights or it'll just, oh yeah, just block that out there. There you go. You can hold your hand there. So what I'm going to do is this. I'm going to take one end of my electrical lead and I'm going to hook there. Now I want you to look at what's going to happen. The electricity is going to come flowing in. It's going to flow through this light bulb, and then it's going to come through, hang a couple of corners here, and go back through this light bulb. So it's called a series because the electricity only flows in one direction. Think of electricity as like water flowing through a pipe. So here comes electricity, na-na-na-na, through this light bulb, na-na-na-na-na, and on and on. And so I'm going to connect it right here. So what should happen to the brightness of these bulbs? Because now that electricity's got to push its way through two light bulbs. So will the lights get brighter or more dim? Well, let's find out. And I think you can pretty quickly tell that the light bulbs do get dimmer at this point. So what happens is now not only is this battery trying to push electrons through this bulb, this battery is also trying to push electrons through that bulb, and so the bulbs become weaker. Well, we could kind of keep this going a little bit. We could now actually let's make a little zigzag pattern, but this is still a series circuit because the electricity is going to come in, run through this bulb, come around, and back out through this bulb. So now we've got three bulbs. Well, and I've apparently got a technical difficulty. There we go. Now, you can kind of see how some of these bulbs are barely even showing any sign of light whatsoever. It's just a little bit of a brighter bulb here. But the bulbs get even dimmer. So that's a series circuit. A series circuit has one single path for the electricity to flow. A parallel circuit, well, let's do an example. A parallel circuit, let's hook this wire up here like this. So look what's about to happen to the electricity. The electricity is going to come running in here, and it's going to do what? It's going to split. As soon as you see a split like this, you know it's parallel. So what happens? Let's find out. Wow, if you look at this, the bulbs get even brighter than the bulbs would be if there's just one single bulb. So this is fascinating. Instead of getting dimmer, when we put them in parallel with each other, the bulbs actually get brighter. So that kind of leads us into working these problems with series and parallels. Now, I love these problems. Main reason why I love these problems, one simple reason. See if I got my picture here right. I kind of get my camera out of the way. See if I can kind of, yeah, there we go. Main reason why I love these problems, a series problem, I'm going to always do the same three things to start this problem off. So my number one thing that I'm going to do when I go to work this problem, I'm going to establish what the total voltage is in this circuit. Well, that's easy. It's a 6-volt battery. Y'all have to excuse me. I have a cold, it seems like. Anyway, so I've got a 6-volt battery. And now the second thing I'm going to identify, I'm going to try and attempt to identify this R total. So how I can find an R total is easy. For a series circuit, I have an equation just for finding R total. Well, R total is equal to R1 plus R2. Well, heck, if I had 5 R's, it'd be plus R3, plus R4, plus R5. So all I've got to do is add these resistances together. 10 ohms plus 20 ohms. I feel another cough coming. This video is turning out terrible. Add those resistances together, and I've got 30 ohm total resistance. So now I'll come back here and I'll write 30 ohms. And now I want to do one more thing. A big part of this chapter is going to be this. You've got to figure out the current leaving this battery. And by current, I'm referring to I. I represents current. I represents how much electricity, the actual flow of electricity leaving this battery. So what I want to do next is I want to find, step number 3, I want to find this I total. This is beautiful. In any resistor question, once I find R total, the only equation I'm going to use the rest of the problem is this. The only other equation I'm going to use, V equals IR. That's it. That's my one. Every other question I'm going to get is going to be answered with this equation. So V equals IR. It's known as Ohm's law. So if I want to find I total, I just need V total and R total, 6 and 30. So let's see, this would be 6 equals I times 30. 6 divided by 30, 0.2 amps. So I've got 0.2 amps of electricity in this question. I want you to look at what happens. 0.2 amps. That means leaving this battery is 0.2 amps of electricity. Now I want you to play a game. Let's call it follow the electricity. Here comes that 0.2 amps. That 0.2 amps is going to flow through this resistor. So here we got 0.2 amps again. Keep following. Here it comes. It's like water in a pipe. 0.2, 0.2, 0.2. So how many amps is in here? 0.2 amps again. And then it means following back all the way to the battery should be 0.2 amps of electricity anywhere in this problem. Now, here's the thing. This little V in here represents a meter. And what happens is part of your battery is going to get used up over each resistor. Now, I want you to look at this. You've got a 6-volt battery. Which one of these two resistors is it going to be harder to push those electrons through? Well, it's going to be harder to get through this 20 ohm resistor. It's got twice as much resistance as this one. So this voltage, V2, should be twice as high as this voltage, V1. How can I find this voltage, V1? Well, I've already told you. The only equation I'm going to use is V equals IR. So if I want to find V1, I'm going to write V1 equals IR. And now all I need to know is what is I and R underneath V1? Well, I've got 0.2 amps and 10 ohms. So 0.2 times 10, I'm going to lose 2 volts of potential. I'm going to write it right here, 2 volts. I'm going to use up 2 volts of my battery just getting through here. Well, now you can use common sense. I've got a 6-volt battery. I'm losing 2 volts of it on this first resistor. How many volts should this one be? Well, we can either use common sense or we can just plain work it. V2. I wonder what the equation for V2 would be. Let's see. Oh, wait, there's only one equation after we get R total. V equals IR. So V2 is also equal to IR. V2 would be equal to 0.2 times R, which is 20. Wait a second. 0.2 times 20. That's 4. So that means 4 volts is getting used up over the second resistor. See if this makes sense. We can check our answer. 4 plus 2 makes 6 volts. It's kind of great. It pretty much tells me I must have just done this problem right at this point. This is all there is to doing a basic series problem. You just called it right there. Get your V total, get your R total, get your I total, and then follow that I total all the way through the problem, and it'll teach you how to get all your other V's in there. Let's do a parallel problem on this video too, and then we'll do 2 more with a couple of bit harder questions in there. First of all, go ahead and take a look at this parallel circuit. Same resistors, but you saw a little while ago, instead of getting dimmer when we hooked them together, what actually happened? The bulbs actually got brighter. And that's because I want you to look at something. When we find this electricity, follow that electricity again. When that electricity gets to this spot, and we call those junctions, when it gets to this junction, the electricity is going to split. Part of the electricity is going to go this way. Part of the electricity is going to go this way. It's like water flowing through a pipe. Well, you should be able to tell me, where is the bulk of this current? Where's the bulk of this electricity going to flow? Well, you got two clogged pipes, a 10 and a 20. Well, you can take a look. Where should it flow? Electricity always takes the path of least resistance. So here you can see, we should have a lot more electricity flowing in the 10 than we do the 20. Well, that's good and well. But how do you work a parallel problem? Well, let's just do it. Step number one. Step number one in this problem, establish what your voltage total is. Find your V total. Well, that's easy. It's 6 volts for this problem. And I just always like finding that to start off every question. Step number two, find my R total. Now, R total for a series, all you had to do was add them together, R1 plus R2. This is parallel. Well, we've got a different equation for R total for parallel. Take a look. It's 1 over R total equals 1 over R1 plus 1 over R2. Now, the great thing about this equation is we could have 50 of these resistors. And it would be 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 plus on and on and on and on. So I want to do something. This is going to be 1 over 10 plus 1 over 20. Well, we're adding fractions here, so let's see. This would end up being 3 over 20. And this is where a lot of people would be like, yeah, I've got this done, 3 over 20. There's a catch. You have not solved for R total. You have solved for 1 over R total. Meaning R total is not 3 over 20. 1 over R total. You have solved for the reciprocal, the inverse of R total. Which means if you want to find R total, you need to take a reciprocal of 3 over 20. I'm going to put a little negative 1 sign there. Because we're going to take the reciprocal. Well, what's the reciprocal of 3 over 20? 20 over 3. Now, of course, you also, in the calculator, you probably got an X negative 1 button, just like that one you can mash if you want to. But I'm just going to go 20, as soon as I turn it on, 20 divided by 3, what is that? 6.66666. So I'm going to go 6.67 ohms of resistance. So there's my R total. 6.67 ohms of resistance. So there's my answer for R total. Well, a little while ago, I told you I've got 3 priorities. Every time I do one of these problems, I want to find my V total, I want to find my R total. Third, I want to find the I total in this problem. Well, once you have R total, the only equation you're going to use, the rest of the whole problem is just V equals IR. That's it. That is the only equation I'll use. If this problem had 300 resistors in it, once I got R total, this is all I'm going to use. So in this case, my voltage total is 6. My I total is what I'm looking for. And my R total is 6.67. Well, this is not going to be much of a number, 6 over 6.67. So let's see what we get here. 6 divided by 6.67, 0.899. Wow, it is basically 0.9 amps is what we got. Now I want you to look at something. That means leaving this battery is 0.9 amps of electricity. So what's going to happen to that 0.9 amps? Well, it's going to split. Part of this 0.9 is going to go through the top. Part of the 0.9 is going to go through the bottom. Let's call the top I2. And let's call the bottom I3. I thought I was done coughing for a while. Well, geez. What equation can I use to find I2 and I3? Wait a second. There's only one equation good for this problem. V equals IR. So that means V would be equal to I2R. So I've got a 6-volt battery, I2, trying to push, and now this time I want you to look, it's 6 volts pushing through a 10 ohm resistor, which gives me 0.6 amps. So what we have just found is that there are 0.6 amps of electricity flowing through the top of this circuit. Hey, you don't have to be a super duper scientist to figure this out. 0.9 amps came in, 0.6 amps is going to the top, so how many amps are going to the bottom? 0.3 amps. Could we prove it? Well, yeah. 6 volts divided by, oh look, right here, 6 volts divided by 20. That would be 0.3. So we could do V equals IR one more time and prove that I3 is 0.3. But that's all there is to working a basic, simple series and parallel circuit. Thank you for watching.